Most students first meet the imaginary unit as an abstract mathematical concept with no physical meaning. In RF engineering, however, it plays a very concrete role in describing oscillations, phase, and wave behavior. In this lesson, we will understand what the imaginary unit really means in RF systems and why it is not imaginary in practice at all. The imaginary unit exists because real numbers alone are not sufficient to describe two-dimensional relationships in mathematics and physics. When dealing with oscillations, waves, and rotations, a single-axis representation is not enough to capture the full behavior of the system. In RF engineering, signals often involve both magnitude and phase. A purely real representation can only describe amplitude, but cannot encode directional or phase information. The imaginary unit introduces a second independent dimension that allows these two aspects to coexist in a single mathematical structure. This extension is not arbitrary. It is a necessary mathematical tool that enables consistent modeling of rotating and oscillating systems in electrical engineering. The imaginary unit is best understood geometrically rather than algebraically. In the complex plane, the real axis represents horizontal movement, while the imaginary axis represents vertical movement, forming a two-dimensional coordinate system. A value multiplied by the imaginary unit corresponds to a 90-degree rotation in this plane. This geometric interpretation is crucial in RF engineering because it directly connects algebraic operations to physical transformations of signals. Instead of treating the imaginary unit as a purely abstract symbol, it can be interpreted as a tool that represents phase shifts in oscillating systems. In RF systems, sinusoidal signals can be represented as rotating vectors in the complex plane. The imaginary unit allows this rotation to be expressed mathematically in a compact and consistent form. As the vector rotates, its projection onto the real axis produces a measurable sinusoidal waveform. The imaginary component represents the quadrature part of the signal, which is essential for describing phase relationships between multiple signals. This rotating vector interpretation is the foundation for phasor analysis, modulation techniques, and signal processing methods used in communication systems. RF engineers use the imaginary unit, often written as J, because it simplifies the analysis of oscillating systems. Instead of working with time-dependent sine and cosine functions separately, both components can be combined into a single complex expression. This simplifies calculations involving phase shifts, impedance, and wave propagation. It also allows engineers to apply algebraic operations to problems that would otherwise require solving differential equations. The imaginary unit is therefore not a theoretical curiosity, but a practical tool for simplifying real engineering problems in RF system design. In RF engineering, the imaginary unit appears in almost every core concept, including impedance, phasors, modulation, and frequency domain analysis. It enables engineers to represent phase differences naturally and consistently across all parts of a system. Without the imaginary unit, describing wave behavior in circuits and transmission lines would require significantly more complex time domain equations. By introducing a second dimension, RF analysis becomes structured, scalable, and mathematically efficient. Understanding the meaning of the imaginary unit is essential before moving into Euler's formula and phasor representation. In this lesson, we learned that the imaginary unit is not just an abstract mathematical symbol, but a representation of a second dimension used to describe phase and rotation in RF systems. It allows engineers to model oscillations, signals, and wave behavior in a unified mathematical framework. In the next lesson, we will explore Euler's formula and see how it connects complex numbers with sinusoidal signals. If you found this useful, like the video, subscribe, and follow for the next lesson.